A very good morning to all of you. We were discussing electromagnetic induction and we continue with our discussions on the Faraday's laws of induction. Remember, we have seen that whenever there is a change of magnetic flux through any closed path, there is an induced EMF in the closed path, and if there is a conductor in that path, then the EMF generates a current in that path. So, we had seen how the change of flux generates induced currents. So, we are looking at one example just as we finished the last class, and the example was the motional EMF. So, we had seen that there was, if I assume a magnetic field pointing downward, and if I consider a conductor, fixed conductor placed like this, and there is another conductor on this which is moving to the right with a velocity v, then we found that as the conductor moves, then there is an induced EMF generated, and we had interpreted this as if, because when the conductor moves, the free electrons in the conductor are moving, the motion of the free electrons in the magnetic field generates a force on the free electrons. So, because the velocity is in this direction, magnetic field is pointing downward, the V cross B is upward, because the electrons have a negative charge, they are pushed down, and the electrons then follow this path, and so there is a current generated. The electrons are flowing in this clockwise direction, so that leads to a current in the anti-clockwise direction. So, there is a induced EMF leading to a current in this direction as shown here. So, we had interpreted this from this EMF from the Lorentz force law, because the conductor motion creates Lorentz force on the electrons within the conductor, and that Lorentz force leads to a flow of electrons in the circuit, and that flow of electrons constitutes a current. Now, I had mentioned in the last lecture that the same EMF could be derived from the basis of Faraday's law of induction. So, let us see how that can be done. So, you see here the magnetic field is B, we assume a uniform magnetic field. So, if I assume this length is, this distance is x, the magnetic flux phi b is equal to B into this area, which is x times L, this distance is assumed to be L, so x times L. So, at any given instant of time, the magnetic flux through this closed path is B times x times L. So, if this conductor moves with a velocity v, the rate of change of flux is equal to d phi b by dt, which is equal to B times L times dx by dt, and dx by dt is nothing but the velocity of the rod with which it is moving. So, we get a rate of change of flux to be given by this. So, according to Faraday's law of induction, the induced EMF minus d phi by dt, which is equal to minus B times L times B. So, because the flux I am calculating, again the magnetic field is pointing downward, the flux I am writing as positive. So, the induced EMF calculation must be in this direction, and I get a negative value for induced EMF, which constitutes a current in the anti-clockwise direction. And if you recall back in the earlier lecture, we had obtained the same induced EMF using Lorentz force law. So, these are two representations of the same induced EMF. In the case of conductor motion, in the case of motional EMF, I can interpret the induced EMF as if coming from Lorentz force law. But please remember, if I keep the same situation here, do not move the rod, but if I change the magnetic field with time, then there is again an induced EMF generated in this circuit in the conducting path, and that induced EMF is cannot be interpreted as Lorentz force, because there is no motion of electrons, and immediately only the magnetic field is changing and it induces an EMF. So, that induced EMF is generated essentially by the change of flux in this. So, that is a more general law that whenever there is a change of magnetic flux through a closed path, there is an induced EMF generated in the closed path. If the closed path contains a conductor along the path, then there is a current generated in that closed path. If there is no path, if there is no conducting path in that, then in free space a changing magnetic field will immediately generate an electric field like we had seen last time. So, this is a very general and important law in electrodynamics, essentially Faraday's law of induction. Now, look at the direction of the induced EMF and the current is flowing like this. So, the induced EMF is like this, and as we saw last time, this current, that means in this conductor there is a current flowing in the upward direction, magnetic field is downward. So, there must be a magnetic force on the current carrying conductor, which is I L cross B, we have seen before. So, the magnetic force F B is equal to I L cross B. Now, in this case L vector is perpendicular to B vector. So, this is nothing but I L B, the magnetic force magnitude is I L B, and what is the direction? L cross B. So, L is up because the current is flowing in this direction. So, L vector is upward like this, B is downward, and so L cross B. So, the magnetic force is in this direction. So, the wire is being pulled back towards the this side. So, I am trying to move it away from the to the right direction. There is a magnetic force to the left, and this magnetic force also comes from the fact that the induced EMF has minus BLV, which means the current is flowing like this. So, remember this negative sign we had introduced in the beginning as Lenz's law, that the induced EMF is always so as to oppose any change in the flux in the loop. Now, we can also see this from physical principles that there must be a negative sign here. Suppose imagine a situation where the induced EMF was clockwise and not anti-clockwise. So, when I try to move this rod to the right, imagine a situation where the negative sign did not exist, that means the EMF would have been in this direction. So, then in that case in this rod the current would have been flowing down and the magnetic force would have been to the right. Now, the problem with this is that suppose I give the rod a small push to the right, the magnetic flux starts to change, and if the induced current is in the downward direction, this will result in a magnetic force to the right side, which will increase the speed of the rod, which will increase its velocity. So, as the velocity increases, the rate of change of flux increases, the induced EMF even increases further, increasing to a greater force, and this goes on increasing indefinitely. Obviously, this is not a physical situation. So, even from this consideration we can see that there must be a negative sign here, which is essentially Lenz's law. So, Lenz's law just comes out of the fact that energy conservation is required, and when I try to move this rod to the right, there is a magnetic force to the left. If I try to move the rod to the left, there is a magnetic force to the right. So, I have always to do work against the magnetic force to move the rod, and this is what is essentially Lenz's law. So, this will essentially ensure that the induced EMF is in the direction of minus d phi by dt. Now, let me look at an example and put some numbers into the calculation here. So, let me look at an example. So, let me assume the uniform magnetic field again pointing down. These are my conducting rods. And this distance is L. So, let me as an example take a magnetic field B of 0.5 Tesla. Let me assume a length L of 10 centimeters, which is 0.1 meters. Let me assume a velocity of this to be equal to 2 meters per second. Suppose I am trying to pull it at the rate of 2 meters per second, and let me assume the resistance of this loop is 0.05 ohms. So, I have a situation like this in a uniform magnetic field which is pointing downward with 0.5 Tesla. This length I am assuming to be about 0.1 meter, 10 centimeters, and I am trying to pull this at a uniform speed of 2 meters per second to the right. And let me assume, as I mentioned before, the resistance primarily is here and there is no resistance of this part of the circuit. So, the resistance remains constant at 0.05 ohms. So, what is the induced EMF? E is equal to B times L times B, which we have just derived, which is equal to 0.5 Tesla into 0.1 meters into 2 meters per second, which is about 0.1 volt. So, there is an induced EMF of 0.1 volt across the circuit here, and this induced EMF comes in because I am trying to pull the rod to the right, and this is an induced EMF. And this induced EMF will generate a current I is equal to E by R, which is equal to 0.1 by 0.05 ohms, which is about 2 amperes. So, there will be a current of 2 amperes, the resistance is only 0.05 ohms I am assuming. So, there is a current of 2 amperes generated in this. Now, this current, as we saw before, will generate a force, magnetic force to the left side, and I can also calculate the magnetic force on this rod. Magnetic force on the rod, which is equal to I times L times B, which is equal to 2 amperes times 0.1 meters times 0.5 Tesla, which is equal to 0.1 Newton. So, there is a force on this rod of 0.1 Newton to the left side. So, if I keep the velocity constant at 2 meter per second, I need to apply a force of 0.1 Newton to the right to keep the velocity constant at 2 meter per second. Otherwise, the magnetic field which is inducing this EMF is trying to pull that rod back in the reverse direction. So, that is an example which gave me some kind of a numbers which are involved in this process. Now, till now what we have been doing is we have been assuming a certain conducting path and calculating what is the induced EMF in that path, and if there is a conducting path in there, there is a current generated and we are calculating the current. Now, many situations what happens is there is no conducting wire there, but there is a conducting solid. So, if I have a conducting solid in a changing magnetic field, then in the conducting solid there will be currents generated just like currents in a conducting path, because as we have seen, a changing magnetic field will generate an electric field, and this electric field will then try to move the charges within the conductor, and that will lead to a current. So, there are these are called eddy currents. So, whenever you have a conducting material which is subjected to a changing magnetic flux, then induced current gets generated throughout the volume of the conductor. So, if you had a wire, the conducting path is essentially determined by a line and the current flows along that line, but if you have a solid conductor, then the induced electric fields will tend to generate a current right through the volume of the conductor, and these are called eddy currents because these currents resemble eddies in water, and so they are called eddy currents. In fact, remember the demonstration that we had done in the beginning of the course, in the beginning of the discussion of magnetostatics. I had taken a solenoid, a wound solenoid here, and then we had a soft iron piece inside through the hole of the solenoid here, and then we had essentially an aluminum disc sitting on it, and I had shown that if you change the current if you had applied an AC current through this, then what happens is the current in the coil changes with time. That changes the magnetic field generated by the solenoid with time, and that solenoid, this changing magnetic field will induce a current in this conducting aluminum sheet here, and what we saw is essentially this is the sheet here. So, this is the sheet here, and we saw that the eddy currents actually lead to a repulsion, because induced EMF is always so as to oppose changes. So, as the magnetic field is changing with time, there is a induced EMF in the entire volume of this aluminum disc, which essentially pushes the aluminum disc upwards, and we saw a levitation. So, depending on the magnitude of the rate of change of flux, the force on this will be different, and you can actually raise it to different heights, and that is essentially very interesting concept of magnetic levitation. Now, eddy currents also can happen in other situations. For example, let me draw another figure which I will show you another kind of eddy current. So, you have, so essentially what is happening is, suppose I had a conducting surface here, suppose I had a conducting surface, a solid conducting here, and if I had a solenoid carrying current, the solenoid will have its own magnetic flux surroundings. So, as I bring the solenoid closer and closer, and if I change the magnetic field of the solenoid, which means by changing the current passing through the solenoid, I will generate eddy current like this in this path. In the volume of the conductor here, this is the conductor here, and in the volume of the conductor I will generate eddy currents. They will circulate like this, because the changing magnetic field generates electric fields, and those electric fields then drive the electrons within this conductor, leading to eddy currents. So, these are the currents that will get generated within the solid, and this is exactly what is happening in this case of the demonstration that I showed you. There are eddy currents generated in this, and those eddy currents are responsible for the effective magnetic repulsion of the solid with respect to this. Now, in fact, what is happening is, you may have noticed that this was not a solid rod, it consisted of a large number of small rods here. There were a large number of rods actually, and the reason is the following. So, suppose I had a solid rod like this, in which the magnetic field was pointing like this and changing with time, then you will see induced currents like this everywhere, and these induced currents, as they pass through this eddy currents, as they pass through the solid conductor, will lead to essentially a heating, because the solid conductor has some resistance. So, as the currents pass through the solid conductor, they will generate heat, and the energy that I am feeding actually partly gets converted to heat in this conductor. I can actually reduce this effect by using what are called as laminated. So, if I take, instead of a single piece, I take a larger number of these cylindrical rods, smaller diameter rods forming the same diameter, overall diameter as before, then what will happen is, the eddy currents have no path to get completed, and so the amount of eddy current generated in this situation becomes much reduced. So, this is called lamination, and I can do a lamination to reduce effects of eddy currents by breaking up the entire solid into smaller pieces, and in that situation this can help me to reduce any eddy current losses in the device. And this is precisely used in transformers to have instead of a solid core, you have laminated core, which essentially ensures that the eddy currents do not have a path to complete themselves, and so the amount of eddy current generated gets reduced, and that leads to a reduction in overall heating of the core. There is another very interesting demonstration that could be done, and that is the following. So, suppose I had again a magnetic field pointing downward, a uniform magnetic, say, pointing downward in this space. So, let me assume that I have a copper plate which is pivoted like this and which oscillates like this. So, I have a copper, this is a copper plate here hanging on a this thing solid, and on a wire here, and this is oscillating like this. Now, imagine what happens as this copper plate enters the magnetic field, the magnetic flux through this changes, the magnetic field applied on this conductor changes, and that induces an EMF, and eddy currents are generated. So, as this enters inside, the magnetic flux is increasing, and so the eddy current will be such as to counter this increase in magnetic flux. So, magnetic field generated by this should be opposite to the direction of this magnetic field, which must be upwards. So, it will generate an induced current in this direction. So, please note, as the solid moves into the magnetic field is increasing with time, the magnetic flux is increasing with time. So, the induced EMF will be such as to reduce this increase, which means that the currents generated in the solid must be so as to oppose this magnetic field, which means that they must generate a magnetic field which is pointing upward, because this magnetic field is pointing downward, and that will be generated if a current is flowing like this. So, what happens is, this current starts to flow in this direction, and as the solid copper piece enters this magnetic field, and once it has fully entered, there is no change in magnetic flux and there is no effect until the solid copper piece starts to exit the magnetic field. Now, what will happen is, as the plate exits the magnetic field, the magnetic flux is decreasing with time, and so the induced current in this must counter this effect, which means it must generate a magnetic field which is pointing downward, and that means the current must be in this direction. So, that this current produces a magnetic field pointing downward, and it actually leads to an eddy current in this direction. Now, what happens in this case is there is a force which is acted upon, because there are currents here, there are magnetic fields. This current actually, this force, magnetic force, tries to put a friction on the movement of this plate, and this is essentially the plate will not oscillate freely, and it will be damped into a very quick stop of into the magnetic field. So, it is a very interesting example, again a very nice demonstration that can be shown to show the effects of induced EMFs. Now, there are many applications of this induced EMF. So, let me note down some of them. They are used in magnetic braking, in trains, because they provide a restoring a force in the opposite direction. So, they can be used to brake. They are also used in electric motors. They are used as induction furnaces. Remember, I mentioned to you that these currents, as they pass through the material, the conductor, they will generate heating because of Joule heating, and that heating can be used for making a furnace. They are also used as metal detectors. For example, at airports, where you have seen that there are detectors which detect presence of metals, and this can be based on induction. And I must mention that there are some undesirable effects, and the undesirable effect is essentially that it causes heating in transformer cores, and as I just now mentioned, this can be reduced by laminating the core. So, for example, in this plate, in this experiment, if I had, instead of doing this, if I had, let me draw another figure here on the side. So, if I had a situation in which the plate was not a solid plate like this, but say was laminated. So, for example, if I had a plate and this plate was like this, then what happens is you have sort of destroyed the path for the induction, for the EMF to generate currents. The eddy currents get much reduced, and the damping is much reduced here, because the eddy currents gets reduced. So, instead of having a solid piece like this, if you had cut pieces, you can reduce the effect of eddy currents, and that is what essentially is done in lamination of the core of a transformer, where you can reduce the effects of eddy currents. So, there are many applications, we will discuss a little later also again, but there are many applications of these induced EMFs which are very useful in practical situations. Now, this induction leads to electromagnetic induction leads to another very important concept, that is concept of inductance. So, let me assume that I have two coils placed close to each other. So, let me call this this is loop 1 and this is loop 2. Now, I pass a current through this loop. Suppose I pass a current through this loop. This will have a magnetic field associated with this. So, the magnetic field may be generated like this. So, when I pass a current through this loop 1, I will generate a magnetic field because of this current. There is a loop which is placed close to this loop 1, which I call loop 2. So, the part of the magnetic flux will pass through this loop 2, and so the loop 2 will enclose certain kind of a flux. Now, notice that the magnetic field produced by loop 1 is proportional to the current passing through loop 1. So, suppose I call the current I 1. Remember, the magnetic field produced by this current is mu naught I 1 by 4 pi integral over loop 1 d L 1 cross R by R cube. We have seen Biot-Savart law before. So, the magnetic field produced by this loop 1 is given by this and is proportional to I 1, and so the flux through loop 2, which is equal to the magnetic field into this area, actual integration of B dot T A. So, this is B dot T A over loop 2 will be proportional to I 1. Note here, so B 1 dot D A 2. So, I am integrating over the area of loop 2. The magnetic field produced by the loop 1, current I 1 in loop 1 is B 1. Loop 2 is placed somewhere close to loop 1. So, some of the magnetic field lines generated by loop 1 pass through loop 2. The magnetic field generated by loop 1 is proportional to current I 1 passing through loop 1, and so the magnetic flux passing through loop 2 is proportional to the current passing through I 1. So, I can write a relationship flux through 2 is equal to M 2 1 I 1, where M 2 1 is a constant of proportionality and is called mutual inductance. It is called mutual inductance. It is mutual inductance because it is how much flux is linked by loop 2 because of current in loop 1. So, it is a mutual relationship here between these two loops, and M 2 1 actually is a constant which depends on the orientation of the two loops, the position of the loops, the geometry, the shape, etc., etc. So, this is a quantity which depends on the position and orientation, area, etc., shapes of the loops, but this is a constant, and the flux passing through the second coil loop 2 is proportional to current passing through through the loop 1, and this proportionality constant is called mutual inductance, and this is a very important quantity. So, let me look at an example of this mutual inductance. To understand mutual inductance, let me look at an example of two coaxial long solenoids. So, I have one big solenoid like this with the coil, and I have another solenoid inside with another coil here. So, let me call this solenoid S 1, this solenoid S 2. So, I have solenoid S 1. So, number of turns per unit length, L 1, radius of S 1 is R1. Solenoid S2, number of turns per unit length, sorry, this is N1, N2, and radius of S2 is R2. So, N1 turns per unit length for solenoid S1 of radius R1, N2 turns per unit length of turns for solenoid S2 and of radius R2. Now, let me assume that I pass a current, I1 through S1. So, I have this S1 is connected to a current source. First of all, I am assuming that these are very long solenoids. So, I can assume the magnetic field generated by these solenoids is uniform within the solenoid, and this S1 has now carrying a current I1. So, magnetic field produced by S1 is equal to mu naught N1 I1, and this is within the solenoid. Of course, I must remember that this magnetic field is generated within the solenoid S1, and there is no magnetic field outside the solenoid of S1 when the current is passing through S1. So, now please remember the solenoid S2 is surrounding solenoid S1. So, the magnetic field generated by S1 forms a part of magnetic flux that is crossing S2. So, magnetic flux is now, because of the magnetic field generated by S1, there is a magnetic flux through S2. So, what is the magnetic flux? Magnetic flux through each loop of S2, which is equal to the magnetic field mu naught N1 I1 into this area only, because although S2 is bigger, there is no magnetic field outside between S1 and S2, the magnetic field only exists within S1. So, the flux is calculated by magnetic field times area, but the area in which magnetic field exists only in this region. So, this must be equal to into pi R1 square. Please note, although the area of S2 is pi R2 square, the magnetic field occupies only an area pi R1 square within the solenoid S2, and that magnetic field is uniform. So, every loop of S2 has a flux of mu naught N1 I1 into pi R1 square through the solenoid S2. So, the flux through length L of solenoid of which is equal to, so this is magnetic flux through every turn N1 I1 pi R1 square into the number of turns in a length L, which is N2 times L. So, this is equal to mu naught N1 N2 pi R1 square L into I1. So, this is, I will write this as M21 I1, where in this example M21 happens to be mu naught N1 N2 pi R1 square to L. So, that is the mutual inductance between these two solenoids. So, all it means is that when I have a current I1 passing through S1, then over a length L, the flux passing through solenoid S2 is simply M21 times I1, and M21 for this example happens to be mu naught N1 into pi R1 square into L, and that is the mutual inductance between these two coils. And it depends on, as you have seen here, it depends on the number of turns per unit length of solenoid S1, the number of turns per unit length of solenoid S2, the area of the solenoid S1, and the length of the entire device that I am looking at. So, I can define here mutual inductance per unit length as mu naught N1 N2 pi R1 square. Now, so what happens, suppose I pass a current I through the outer solenoid instead of the inner solenoid. So, I can also again associate a flux enclosed by S1 because of a current in S2, then I will get another mutual inductance. So, for example, if I pass a current I2 through S2, so current I2 through S2 then what I will get is the magnetic field generated is equal to mu naught N2 I2. Mu naught N2 I2 is the magnetic field generated by S2. Now, that magnetic field is part of the flux is passing through S1. So, S1 now encloses a certain flux and there is a mutual inductance between S1 and S2 when I pass a current through S2. So, what is that? Let me calculate. So, flux through each loop of S1 which is equal to mu naught N2 I2 into look here, the flux through S1 depends only on area of S1 which is pi r1 square. So, the magnetic field lies inside and outside S1. When I pass a current I2 through S2, there is a magnetic field generated within the entire solenoid S2, but the flux that is linked by S1 is only in this area. So, that is equal to the magnetic field into area. So, flux through a length L of S1 is equal to the flux through each loop into N1 into L. N1 is the number of turns per unit length multiplied by the length, and this is so this is equal to mu naught N1 N2 pi r1 square L I2, which I write as M12 I2, where M12 is the mutual inductance which is mu naught N1 N2 pi r1 square. So, that is the mutual inductance between 2 and 1. This is the mutual inductance I get when I pass a current I2 through S2, and the mutual inductance which I got when I pass a current I1 through S1 is essentially this quantity, and as you can see here they are exactly the same. M21 is equal to M12. So, the mutual inductance between these two coils. So, if I pass a current I through S1, the flux magnetic flux enclosed by S2 is M21 M21 into I1. If I pass the same current through S2, the flux enclosed by S1 is the same because the proportionality constant M12 and M21 are exactly equal. So, let me repeat, if I pass a current through S1, S2 encloses a flux which is proportional to the current passing through S1, and the proportionality constant I called it M21. If I pass the same current through S2, S1 now encloses a flux and that flux is proportional to current I2 passing through S2, and the proportionality constant I called as M12, and both these are exactly equal. So, M12 is equal to M21. So, that is a very important relationship. Now, although I have shown this for this example of a pair of solenoids, one can in general prove this result, that the mutual inductance between these two coils is a fixed quantity, and so I have this proportionality constant is M, it is called M. So, I can also write M12 is equal to M21 is equal to some mutual inductance M. It does not depend on whether I pass a current through I1 through S1 and look at S2, or I pass a current through S2 and look at I1. So, this is a very useful result. So, let me give you an example where this equality becomes very useful. So, let me look at an example. So, let me assume I have a solenoid like this, a very long solenoid, and I place inside this a short solenoid. Now, my objective is to calculate the flux enclosed by the outer solenoid when I pass a current through the inner solenoid. So, I pass a current through the inner solenoid. So, I want to calculate the mutual inductance. So, I want to find out what is the flux enclosed by the outer solenoid when I pass a current I through the inner solenoid. Now, you see here the problem becomes quite complicated, because this solenoid is not an infinitely long solenoid. It will generate its magnetic field like this. So, each loop of the outer solenoid is enclosing different amounts of magnetic fluxes and so on. So, this becomes a very complicated problem, but I can use this relationship that M12 is equal to M21, and this I will get the same relationship if I pass the same current through the outer solenoid and calculate what is the flux enclosed by the inner solenoid. I must calculate the flux enclosed by the outer solenoid when I pass a current through the inner solenoid. That problem is a little complicated. So, I can use the relationship that M12 is equal to M21, and I pass the same current through the outer solenoid and I calculate the flux enclosed by the inner solenoid, because that is much easier. So, for example, if I pass a current I through the outer solenoid, and if I let me write this as, this is NL, number of turns per unit length, and this is NS, number of turns per unit length of the shorter solenoid. Let me assume this length is L, and let me assume that this radius is long solenoid is RL and the short solenoid has the radius RS. So, the number of turns per unit length of the shorter solenoid is NS, then radius of the inner solenoid is RS and RL. So, the current, for a current I through the outer solenoid, the magnetic field is equal to mu naught NL I, mu naught times the number of turns per unit length times the current. So, the magnetic flux, so this, please remember now, this magnetic field is uniform within the outer solenoid, and this inner solenoid occupies a certain area of this, and so the flux through the shorter solenoid, the smaller solenoid, is equal to the magnetic field into the area into the number of turns, which is Ns into L. So, this is the magnetic field, that is the area, this is the magnetic field, this is the area, and the number of turns, total number of turns. Please remember that this flux is per turn and there are so many turns. So, this is equal to mu naught N L N S pi R S square into L into I. So, I get an expression for mutual inductance between these two, M is equal to mu naught N L N S pi R S square. So, this relationship is very useful here, because if I were to calculate the mutual inductance between these two solenoids, when I pass a current I through the inner smaller solenoid, it would have been very difficult for me, because the magnetic field is not uniform and different loops of the outer solenoid have different fluxes passing through them, and that would have been a very complex problem. So, I have solved the problem by using the fact that M12 is equal to M21, and that has given me a very simple solution to this problem. So, this is a very important relationship in mutual inductance and can be very useful in certain situations. So, when there is a flux enclosed, by the by one circuit because of the other. So, let me recall this. So, when I have when I have a flux passing through this. So, according to Faraday's law, a changing current in one of these coils should induce an EMF. So, changing current through say loop 1 will induce an EMF in loop 2. So, if I had loop 1 here, another loop 2, and if I change the current here as a function of time, that will induce an EMF in the second loop, and that induced EMF will be equal to minus d phi 2 by dt, which is equal to minus m times d I 1, because phi 2, the magnetic flux, is equal to m into I 1, where m is the mutual inductance. So, if I have a loop here and another loop here, if I change the current in this loop, so if I have a current I 1 passing through this, and if I change the current, then this current actually leads to a flux, magnetic flux of m times I 1 in this loop, and when I change the current, that induces an EMF in the second loop, and that is given by minus m di by di 1 by dt, and that is a very important relationship when I look at circuits in which there are multiple loops present. So, the induced EMF is a relationship that we must remember, this is equal to m times minus m times di 1 by dt when there are two loops placed close by. Now, having seen mutual inductance, we see that there is another important concept which is also called self inductance. So, let me again take a solenoid, a long solenoid, and I pass a current through the solenoid. Okay. Now, when I pass a current through the solenoid, there is a magnetic field generated by the solenoid, and for example, these loops are also encircling those magnetic fields. So, the magnetic field generated by the solenoid is also forming a part of the flux that is passing through the same solenoid. So, suppose let me assume that the number of turns per unit length is equal to n and current is equal to I, then the magnetic field is equal to mu naught n I. So, each loop of solenoid will have a flux mu naught n I into, if I assume the radius of the solenoid to be r, pi r square. So, each loop of the solenoid will have a flux passing through this so much. So, total flux, total magnetic flux through a length L of the solenoid is equal to phi times the number of turns, which is n times L. So, let me calculate this again. So, this is the total flux passing now is equal to phi times n times L, which is equal to mu naught n I pi r square into n times L, which is equal to mu naught n square pi r square L into I. Now, I call this as L times I, where L is equal to mu naught n square pi r square into L in this example. This is called self inductance. It is called self inductance because it is the flux through a coil, flux through the solenoid, the magnetic flux passing through the solenoid because of a current passing through the same solenoid is nothing but proportional to the current passing through the solenoid, and that proportionality constant is called self inductance, and in this case it comes out to be mu naught n square pi r square into L, and this is a very important part of a coil like this, and this is the this self inductance defines how much is the flux passing through the solenoid if I pass a current through the solenoid, say same solenoid. Now if I change the current in the solenoid, if I change the current passing through the solenoid, then we see that this, if I change I with time, this will induce an EMF in the coil itself, because when I change the current through the solenoid, I will change the flux passing through the same solenoid, and that change of flux will lead to an EMF, and the EMF, generated EMF, minus d phi by dt is equal to minus L di by dt. So that is induced EMF. So whenever I try to change the current through the solenoid, there will be an induced EMF generated in the solenoid, and by Lenz's law, that induced EMF will try to generate a current to oppose this change. And so for example, if this current passing through the solenoid produces a magnetic field pointing upwards and the current is increasing, the magnetic flux in the upward direction is increasing with time. So the induced EMF will be such as to generate a current in the reverse direction to reduce the flux, to reduce the change in flux, to reduce the increase in flux. So it will try to oppose any increase in flux, and it is kind of a resistance to the change of flux. It is giving a resistance to my increasing current. If I try to increase the current, it sort of tries to maintain the current as before. Similarly, if I try to reduce the current, I will reduce the flux passing through the same solenoid, and the induced current will be such as to oppose this change, will try to maintain the flux as before. So this induced EMF is also called as back EMF, because it actually tries to reduce the changes that you are trying to impose on the circuit. So if you are trying to change the current in a circuit, that will induce an EMF in the circuit, a back EMF, and that back EMF will be in such a direction, or that will generate a current in such a direction that it will try to oppose this change, and so will not allow this change to take place. So this is a very important part of circuits, and this is called inductance. And so inductance is like capacitance. The capacitance was a device in electrostatic circuits, in electrical circuits, and inductance is a device which is used in magnetic material, magnetic part of the circuit, and this is always a positive quantity. It is always a positive quantity, and self inductance plays the same role as mass in mechanical systems. It is kind of an inertia, it gives an inertia. So larger the value of L, harder it is to change the current. So, whenever we have a coil like this and when we try to change the current in the coil, that will give a back EMF, and that back EMF is opposing the change that you are trying to introduce, and it is like an inertia on the system, and it acts like mass in mechanical systems, depending on if the heavier the object, the greater the force you need to move it. And so, similarly in the case of inductance, it is like an inertia, and it sort of opposes any change that you are trying to do. So, let me look at an example. So, take a long solenoid of so having 100 turns per 10 centimeter. Let me take a radius of 1.6 centimeter. So, I want to calculate self inductance per unit length. So, we had calculated self inductance here. This is the equation. Per unit length will be so L per unit length will be mu naught n square pi r square. So, this is equal to 4 pi 10 to the minus 7 into 100 turns per centimeter, that is per meter is 10 to the power 4. So, that is 10 to the power 8 into pi into 1.6 whole square to 10 to the minus 4 into length is 1 meter, and this is comes out to be is equal to approximately equal to 0.1. Now, let me define this. This H refers to Henry. The unit of inductance is Henry, and 1 Henry is 1 Tesla meter square by ampere. Remember, the inductance is defined through this equation, where the flux is L times I. So, unit of inductance is flux divided by current. Flux is magnetic field into area. So, inductance must be magnetic field into area by current, which is Tesla meter square per ampere. So, that is called Henry, and this is the unit. And so, this particular self inductance which have about 0.1 Henry per meter, and if I were to change the current, if d I by dt is equal to 10 amperes per meter per second, then the induced EMF will be equal to minus L d I by dt, which is equal to minus 0.1 into 10, which is equal to 1 volt per 1 volt. So, that induced an EMF of 1 volt in the solenoid, and that will act against your applied source that you are doing. So, that you are passing the current through. So, that is an example of a self inductance. So, I will stop my lecture here, and we will continue with the discussion on mutual inductance in the next lecture. Thank you very much.